Good morning, everyone. I'm honored to be here at Iceas 2025. My name is Seungmyeong Lee from the Department of Mechanical Engineering at Keimyung University. Today, I'd like to present our research title, Optimization of Electric-Powered Wheelchairs for Last Mile Mobility, Affordable Mobility. This project is the result of close collaboration with my colleague Hae-un Choi, Jihyun Kim, and Jonghyun Kim. Our motivation began with the simple question, how can we make personal mobility more inclusive and accessible, especially for people with physical disabilities? Throughout this presentation, I will walk you through our approach to designing and prototyping a practical and affordable power module that transforms a manual wheelchair into an electric mobility device. Here is a quick overview of today's presentation. I will begin with some background on last mile mobility and challenges faced by individuals with disabilities. Then I will present our research goals and the design principles that guided our solution. Next, I will describe the hardware we developed, including our prototype iterations, control systems, and the test results. Finally, I will conclude with the summary of key findings and outline directions for future development. The entire project was designed with real-world usability in mind, so I hope the demonstration and results will inspire future work in this area. Let's begin with the concept of last mile mobility. This refers to transportation solutions that help individuals travel the final segment of journey, typically from a transportation hub like a subway station or parking lot to their destination, such as their home, school, or office. Various solutions exist. Shared mobility services like e-scooters and bikes, small electric vehicles like neighborhood electric cars, and even walking or shuttle vans. But most of these are not designed with people with physical disabilities in mind. Our project started by identifying that gap. For people with disabilities, electric wheelchairs offer mobility and independence. However, they come with significant drawbacks, short battery ranges, heavy weight, and difficulty with public transport compatibility. Most models are large and difficult to load into a vehicle or carry over curbs or steps. That limits their utility, especially for short or complex trips. We asked ourselves, what if we could make a lightweight modular system that attaches to a manual wheelchair and provides electric propulsion when needed? Our concept is simple: a detachable power module that can be attached by any standard manual wheelchair. The module includes a motor, controller, and battery, all designed to be compact, lightweight, and cost-effective. By combining off-the-shelf components from bicycles, scooters, and micro-mobility markets, we aim to keep the total cost under $300, which this makes it more affordable than conventional electric wheelchairs while still offering electric mobility and portability. The main goal of our research is to design a monowheel drive power module that is easy to control by either the passenger or caregiver, lightweight and portable for storage or loading into a vehicle, affordable using commonly available components. We also focused on making the system intuitive so that elderly users or caregivers could operate it without extensive training or technical knowledge. This is the top view of concept of our monowheel module. It's mounted under or behind the wheelchair and controlled using handlebars that can be pushed forward or tilted left and right. The design eliminates the need for large side motors, which is reduced weight and improves maneuverability in tight spaces. The entire system is designed for modular attachment, so it doesn't require permanent modification to the wheelchair. This is the estimate design of our power system. We assume the total weight of 100 kilograms and the target speed of 6 kilometers per hour. The motor is rated at 250 watts with the 20 to 1 gear ratio. We analyzed whether the system could generate enough torque on a 5-degree slope. As shown in the graphs, both power and current remain stable, and wheel torque increases linearly with the incline angle at 5 degrees. The requirement torque is about 1.8 Newton meters, which is confirmed stable performance in real-world conditions. We built the power system around the brushless DC motor and the lithium-ion battery. The motor is controlled by a PID system with three different modes. Aggressive mode provides fast acceleration suitable for confident users. Moderate mode offers a balanced driving experience. Conservative mode is slower and more stable, ideal for safety in crowded or indoor areas. Users can switch between modes depending on terrain and preference, providing a customizable driving experience. Heat generation is critical for safety and battery life. We analyze motor and battery temperature rise over time during operation. The maximum temperature increase observed was 6.2 degrees Celsius for the motor and only 0.19 degrees Celsius for the battery. These values are well within acceptable limits and ensure that the system operates continuously without overheating in typical usage scenarios. Our first prototype used a lead-acid battery and steel frame for simplicity and low cost. The total cost was about $250. However, the total weight of the module reached 25 kilograms, which made it difficult to handle and mount. While the range was only about 5 kilometers, the power was sufficient at 250 watts, and the steering response provided the core concept. To test usability, we donate the prototype to a local hospital and university. Their feedback was instrumental in identifying design shortcomings such as weight imbalance and limited ranges. The first version was also helped us apply for patents, laying the groundwork for commercialization. The second prototype was redesigned using aluminum frame materials and lithium-ion batteries. This improved both range and weight. Although the cost increased to around $400, it was a necessary step to validate the performance under real-life conditions. This prototype was donated to a local high school and a group of disabled sisters. These donations allowed us to gather diverse feedback, especially for female users and students who use the system of commuting. The third prototype was a breakthrough in terms of cost and performance. Using mass-produced lithium-ion batteries and improved aluminum profiles, we reduced the total cost to under $300 again. This model was donated to a community center for people with disabilities and received positive feedback on ease of use and affordability. Let's watching the video first. We're conducting driving tests to demonstrate steering performance and hill climbing. The monowheel module successfully handled basic slopes and maintained direction with ease. This validated our design's potential not just for flat surfaces, but also for more demanding urban conditions. One of the key strengths of our system is its portability. It fits in the trunk of the standard sedan, allowing users to load and unload it easily. This opens possibilities for multimodal travel, where users drive to a parking lot and then switches to wheelchair mode for the last segment of their journey. In summary, we achieved the following. Reduced cost from 2,000 bucks to under 300 bucks. Reduced weight from 100 kilogram to just 17 kilogram. Increase the range up to 30 kilometer or even more, depending on battery type. Our approach provides a practical and affordable alternative to height-and powered wheelchair. We're currently exploring new features such as motion-based steering using gyroscopes or accelerometers, dual motor systems for more stable driving, improved mechanical design to durability and user comfort. We believe this project can be expanded further to improve mobility for more people in underserved communities. Thank you for your attention to my presentations.